The study of tidal circularization in short-period binaries has been a topic of interest in astrophysics. Previous research has shown that many observed samples of short-period binaries display a cutoff period, PCUT, below which almost all binaries have circular orbits. This feature is likely due to long-term circularization processes induced by tidal interactions between the two stars in each binary. However, the dependence of PCUT on stellar age has been a subject of debate. Using the large sample of spectroscopic orbits from the Gaia DR3 release, the authors have found that PCUT does not depend on stellar age but instead varies with stellar temperature. The cutoff period decreases linearly from 6.5 days at TeF equals 5700 K to 2.5 days at 6800 K. This result is inconsistent with the theory that assumes circularization occurs during the stellar main sequence phase. The authors used a new algorithm to derive PCUT, which relies on the clear upper envelopes displayed in the period-eccentricity diagrams. They applied this technique to a few subsamples of the Gaia SB1s, focusing on binaries with main sequence A, F, and G primaries. The results show a clear dependence of PCUT on the stellar temperature of each bin. The study also discusses the implications of these findings, suggesting that the circularization has probably taken place at the premain sequence phase, as suggested by previous research. The weak dependence of PCUT on cluster age is not significant, and/or might be due to the different temperatures of the samples. The authors used a piecewise asymptotic function to present an upper envelope for the eccentricity as a function of the period for a given sample. This function marks the edge of the populated part of the period-eccentricity plane. They used the Mazeh et al. 2016 algorithm to find the best upper envelope by a maximum likelihood approach, given a sample of spectroscopic binaries. The study highlights the importance of considering the stellar temperature when studying tidal circularization in short-period binaries. The results have far-reaching implications for the theory of binary and exoplanet circularization, synchronization, and alignment. Here is a combined summary of pages 3 and 4 of the research paper. The period-eccentricity diagram for the cleaned MSSB1 sample is presented in Figure 2, which reveals a characteristic tidal circularization pattern. To investigate the reliability of the derived eccentricities, the ratio between the derived eccentricities and their corresponding uncertainties is plotted as a function of orbital period in Figure 3. Two emerging clusters are identified using Kamian's clustering, and a sample of 10,325 binaries with well-constrained eccentricities is defined, along with 7,149 binaries with unconstrained eccentricities. The two subsamples are presented in Figure 4, where the dense area of near-circular binaries is populated by the unconstrained eccentricity sources only. The age-effective temperature dependence of each subsample is plotted in Figure 5, showing a strong correlation between effective temperature and age, with no apparent age difference. The authors then focus on analyzing the subsample of 10,325 binaries with well-constrained eccentricities, deriving the dependence of P_cut on stellar temperature. An upper envelope is defined in equation 2 to characterize the period-eccentricity diagram, where P_cut is the cutoff period and tau is a dimensionless parameter determining the slope of the envelope. The function has two free parameters, P_cut and tau, which define both the separation between circular and eccentric orbits and the location of the upper envelope. The role of tau is further explained, and a modified Fermi function is used to describe the assumed probability density function, PDF, of binaries above and below the upper envelope in the log p, e, plane. The PDF converges to 0 above the envelope and to a positive constant below it, with a transition region characterized by a parameter delta. The probability density at a point, log p, e, is a function of its distance to the envelope curve along the log p axis, expressed in equation 3. The paper presents a novel approach to understanding the tidal circularization of binary star systems, particularly focusing on the relationship between orbital period and eccentricity. It introduces an upper envelope function that describes the maximum possible eccentricity for a given period, which is essential for understanding the tidal interactions in close binaries. This function is derived using a statistical method, assuming a flat distribution of initial eccentricities and periods. To test the algorithm, the authors simulate 6 binary samples with different circularization efficacy coefficients, each containing 500 binaries. The results show that the separation between circular and eccentric orbits is not a straight line but has a curved shape, supporting the use of an upper envelope to characterize the period-eccentricity relation. The best fit parameters obtained from these simulations do not depend on the number of binaries in the sample, only the uncertainties of the parameters do. The paper also explores the relationship between the cutoff period and the circularization parameter, finding a tight linear relation. This implies that the cutoff period is proportional to the circularization parameter to the power of 16/3. This can be traced back to the logarithmic derivative of the eccentricity, which is approximated by 1e for small eccentricities. The algorithm is applied to a sample of 4,430 binaries with orbital periods shorter than 30 days, and the best fit upper envelope is derived. The likelihood of a given sample of binaries is calculated, and the results are presented in Table 1 and Figure 6. The analysis shows that the upper envelope is a good representation of the tidal circularization process, with the cutoff period being the period for which the eccentricity change is approximately 1 during the lifetime of the binary. In conclusion, the paper introduces a new statistical method for understanding tidal circularization in close binaries, providing insights into the relationship between orbital period and eccentricity. The proposed upper envelope function accurately describes the maximum possible eccentricity for a given period, and its application to simulated and real-world datasets demonstrates its effectiveness. Here is a combined summary of the 2 pages, approximately 300 words, in a highly technical and professional tone. The study investigates the dependence of the cutoff period, PCUT, on stellar effective temperature in MS binaries. A histogram of stellar temperatures of 4,376 orbits is shown in Figure 9. The authors divide the binaries into 18 temperature bins and fit an upper envelope to each subsample using their algorithm. The results are summarized in Table 2 and Figure 11. The figure and table offer several features. PCUT drops linearity from 6.5 days to 2.5 days when moving from TEF of 5,500 to 6,800. The linear model for the 13 bins is given by equation 10. The linear fit is quite tight, suggesting that the uncertainties in PCUT are overestimated by a factor of 1.7. PCUT is flat at the 77,006,800 range, approximately 3 days, and might be also flat at 56,005,300 A possible small jump of PCUT might be seen at the Kraft, 1967, break of 6,100 K. The authors find a strong correlation between PCUT and tau of the 18 bins, where tau is the shape of the different upper envelopes. The correlation reflects the fact that all reach the same eccentricity at a period of approximately 30 days. This can be explained by the fact that binaries with such relatively long periods retain their primordial eccentricities and therefore do not show any dependence on TEF. The study concludes that the dependence of PCUT on stellar effective temperature in MS binaries is a complex phenomenon that can be explained by the interplay of several factors, including the shape of the upper envelope, the linear fit, and the correlation between PCUT and tau. The results of this study have implications for our understanding of the dynamics of MS binaries and the role of tidal circularization in shaping their properties. Note: the original text is not provided, so I couldn't include the actual figures and tables. The study examines the tidal circularization of binaries, focusing on the dependence of the cutoff period, PCUT, on stellar temperature and age. The authors analyze a sample of Gaia spectroscopic binaries, dividing them into subsamples based on effective temperature and age. They find that PCUT strongly depends on stellar temperature, decreasing linearly from 6.5 days at 5,700 K to 2.5 days at 6,800 K, with a rate of 3.7 days, 1,000 K. This dependence is evident even when considering the scatter around the linear fit and the uncertainties in PCUT values. The authors attempt to scale the tidal interaction with stellar mass and radius, deriving a theoretical expectation for the dependence of PCUT on stellar temperature. They consider the circularization of stars with radiative envelopes, ignoring the period change associated with eccentricity decay. The approximation of the eccentricity derivative to first order in E is presented, and the authors use Claret and Cunha, 1997, and Van Allen et al. 2016, equations to write the radiative damping parameter, BRAD, as a function of stellar mass, radius, and orbital period. The study finds that BRAD is a monotonic increasing function of stellar mass, implying that PCUT should increase with stellar temperature. However, this is inconsistent with the observed decreasing trend of PCUT with stellar temperature. The authors suggest that this discrepancy may indicate that Zahn's circularization theory is not accurate enough to account for the circularization processes, or that the eccentricity distribution of the binaries was determined during the Permain sequence phase of these stars. The analysis also reveals that PCUT is weakly dependent on stellar age, if at all. The authors discuss potential limitations and assumptions, including the simplification of the circularization process and the neglect of period changes associated with eccentricity decay. They conclude that the study's findings challenge the current understanding of tidal circularization and highlight the need for further research into the underlying mechanisms. The paper explores the tidal circularization of short-period binaries, focusing on the relationship between the orbital period and the tidal circularization period, and its implications for understanding the evolution of closed binary systems. The study uses data from the Gaia mission to analyze a sample of spectroscopic binaries, providing insights into the tidal interaction and its impact on the synchronization and alignment of binary components. It highlights the importance of tidal interaction in the formation and evolution of various types of binaries, including cataclysmic variables, X-ray binaries, and exoplanets. The authors discuss the significance of tidal interaction in the context of the observed statistical features of short-period binaries, emphasizing the need for a more realistic tidal model that accounts for other evolutionary mechanisms, such as magnetic braking and interactions with accretion disks and third companions. They suggest that additional samples of spectroscopic and eclipsing binaries could be used to further investigate the tidal circularization process and its relationship with stellar parameters like mass and age. Moreover, the paper emphasizes the potential of using large photometric surveys, such as ZTF and ASASSN, to identify new samples of eclipsing binaries and derive their circularization periods. The study also highlights the role of tidal interaction in the synchronization and alignment of binaries, which can be inferred from the observed stellar rotation periods obtained from photometric light curves. The authors acknowledge the limitations of their study, including the use of a simplified tidal model and the need for further exploration of the relationship between tidal circularization and other evolutionary mechanisms. They also propose avenues for future research, such as analyzing additional samples of binaries and investigating the tidal interaction in the context of hot Jupiter exoplanets. This paper examines the tidal circularization of short-period binary systems, specifically focusing on the effects of stellar tides on orbital eccentricity. The authors draw upon a comprehensive review of existing literature, citing numerous studies that have investigated the tidal interactions between binary components. The works of Turquim, Martin, and Papalouizou are particularly notable, as they provide a theoretical framework for understanding the tidal circularization process. The authors also consider the observational evidence for tidal circularization, referencing studies such as those by Tunin, Boekholt, and Portuguese-Zwart, which have analyzed the orbital eccentricities of short-period binaries. Furthermore, the authors discuss the importance of considering the effects of stellar evolution on tidal interactions, as highlighted by the work of Torres, Latham, and Quinn. The mathematical framework for tidal circularization is outlined, with a focus on the tidal torque and the resulting changes in orbital eccentricity. The authors reference the seminal work of Zahn, who first described the tidal torque in terms of the tidal quality factor, Q. The equation for the tidal torque is presented, highlighting the dependence on the tidal quality factor, the orbital period, and the stellar radius. The authors also discuss the effects of stellar evolution on tidal interactions, referencing the work of Witt and Savonage, who have investigated the impact of stellar mass loss on tidal circularization. The importance of considering the effects of stellar evolution is emphasized, as it can significantly affect the tidal torque and the resulting changes in orbital eccentricity. The paper concludes by highlighting the need for further research into the tidal circularization of short-period binaries, particularly in the context of stellar evolution. The authors note that a comprehensive understanding of tidal interactions is essential for understanding the evolution of these systems.